So for those of you that have seen my channel before, usually when I have a setup like this, usually it means that I'm going to do something dangerous, and usually I'd start the video out with a warning, then, hey there YouTubers, intro, and so on and so forth. Today, this is the warning, not the normal warning. I'm just telling you because the thing we have constructed is so dangerous that not even a warning and little words will stop you. I'm telling you, don't do it. Period. Do not do it. Okay? So, let's start the intro. Hey there, YouTubers! Professor Sheep here. Welcome to another physics video. As you can see, I'm not wearing my lab coat because we're not in lab. We are out in the field. I have constructed here an air cannon out of PVC pipe. Don't use PVC pipe. When it explodes, it creates shrapnel, and that's not what you want. Use ABC. Is it ABC? I think it's AB plastic, I think. Anyways, so before we actually shoot our projectile, let me show you how this works. So we have a valve here. This allows for where we'll put the projectile in here. We turn this valve, which is connected to the air bladder. The air bladder we will pressurize with this hose. And there's a valve here to stop and start any air. It is open right now. We want it open. There's a pressure gauge. We're putting in 60 psi today. There's this T here, so the air for the air bladder, so it can pressurize the air bladder, and so the air can then go from the air bladder to here. All of it's sealed together with PVC cement, so all good. It does leak. That's because if we go back here, this seal isn't very good. And then I've also trying to just get the seal, trying to get this off. He punctured holes in here. So I'm trying to use some clear Flex Seal to fix that. I'm not sure if it will. I hope it will. So we'll just start off first. So our projectile are some, I think they're the second or third smallest tennis balls you can buy at PetSmart. This one happens to be a nice bright orange basketball, which is good because when it gets shot, it's going to land in that grass and we won't be able to find it, but bright orange we should be able to. So we're going to do two experiments here today, and between each experiment, we'll cut to the math section. And in the math section, I will explain to you what we were trying to calculate here. So the first test we're going to do is if my cameraman can point down range. No board. We're just going to shoot the ball, see how far it goes. And then the next test will be with a board propped up by my ATV. And that'll tell me how far the ball dropped. More specific, it's going to be at 46.5 feet. And the ball, we'll see how far it dropped at that. It's all in the equations. You'll see. We'll see. We'll explain to you. So we're going to load this up first. Alright. Nice and loaded up. So, you're not going to be able to hear me now, so I'm going to hit the switch. So, once that happens, I'll probably cut to what we're about to shoot. So, alright, we're almost at 60 psi. So, please point down range here. Here we go. 3, 2, 1. Alright, we'll go find the ball, then the next cut will be with the board. See you in a bit. So here we are, back in the lab. And before we get into all the math, I just want to say that the measurements we took, and all the measurements we took were not from the video. They were from previous experiments we did before the video. So I realized the way I was going to teach you was, okay, we're going to do this one first, this equation first. But this equation was the second launch I did. So let's skip to the next launch, and then we'll talk about everything all together. So here we are back at the range for our next set of numbers we need for our calculations. So downrange here we have this board. That board's mark is at the same height as this pipe, roughly. So the ball's loaded. I suppose we'll turn this valve on. It's sort of pressurizing. You're not going to hear me, but here we go. Alright, 60 psi, again, level at that board. Downrange, please. 3, 2, 1. Alright, let's walk down there. So, the ball, now we took other measurements earlier, so we're fine. I'm just showing you the ball. Yeah. Right about here, which if we do the math, is probably about 6 inches below our line. But anyways, let's go to the lab and show you the numbers. So we're back in the lab and time for the conclusion. So the second clip you watched with the ball and it dropping, that was for this equation. Now, obviously the drop you saw was different than the drop we did with the measurements. Obviously, because I said 6 inches was the drop on this one, on the one we did earlier was 2 inches. 0.051 meters. So the equation we're going to use is d, distance, equals v initial, which is that, times time, plus 1/2 the acceleration. Acceleration is 9.8, that's gravity. And then times t squared, which is time squared, of course. So the time wasn't very exact because we just had one of my friends, my cousin, used my phone and timed it with a stopwatch. It wasn't very precise at all. We got 1.38 seconds. This was very precise. This was not. And so it threw all of this off. It's all wrong. And our V initial is obviously 0. So that's what the first one was about. My cousin, his brother was like, oh, here's how you should do it. So we went to our next formula, which is this one. Now, this one below is if we shot with an arc. We didn't shoot with an arc, so this one we throw it out. This is no good because we're at a level playing field, or as level as I can get it. So we're up here, which this is 0. I know it's got the little 0 there, but that means nothing. But in our case, this just equals 0. So if we go, and we're going to solve for, that's V initial. Yeah. I'm going to solve for V final. Where's my marker? Here it is, in my pocket. So, basically, if we divide, so we're going to subtract this over, that gets you 0. So it's just x of t over t, which our new time, which we used video editing tricks, we got it to be 0.6 seconds. So if we bring this over, it's 0.6 seconds. And our x of t, which is the distance the ball traveled, was 34.42 meters. That comes out into meters per second, which is 57.367 meters per second. That is surprisingly fast for a ball. Let me grab the ball real quick. Here's our ball. For this ball, same exact ball we used. That, and after doing our conversions, thanks to Google, turns out to be 128.3 miles per hour. Try out running that tennis ball. Fun fact, you won't. And that was only, may I remind you, at 60 PSI. That's not P. PSI. The system, I've put 90 PSI in it before, so I know it can shoot 90 PSI. So just imagine, this is at 2/3 the power, when we could pull it up to 90 PSI, which is basically the maximum I'm willing to go, or maybe even 100, but this is my max power. So we're only at 2/3 power, and the tennis ball is already going 128 miles per hour. What I created myself, is a very dangerous weapon that you should by no means build, or attempt to build. Don't do it, okay? Please be safe, okay? In next week's video, or whenever I get around to doing it, we're going to build a somewhat human-like structure that we're then going to fire this tennis ball at 30 PSI, then 60 PSI, and then 90 PSI. It's a gummy brain. It's not going to simulate human tissue. It's just going to be something fun to do in a video. And there's science, because we're going to find the mass of this ball and using Newton's laws, but Newton's laws are a future video. Using Newton's laws, find the force of the ball when it hits a structure, and to see what it could possibly do to you, and why you should not do this. But in the meantime, I would like to thank you all for watching. Please like, comment, and share. New videos every Friday, and good night. Seriously? You're gonna knock it over prematurely, and you can't even do it right. Oh, you're filming that. Probably should cut that out. But hey, if you like the physics video just watched, and you want to see more, check the link in the description below. And while you're there, hit subscribe. This is a mess. I don't know, I'll just finish it.